Front Range of the Rocky Mountains marks the edge of what was once the great unknown. Forbidding, fascinating, fraught with promise. The scene of explorations familiar to the America of an earlier day. In the shadow of these historic mountains stand the Boulder, Colorado laboratories of the National Bureau of Standards. These laboratories carry on major exploration, seeking new knowledge beyond such modern frontiers as the seething atmosphere of the sun, the bizarre domains of cryogenic cold, the invisible fields of electromagnetism, the unplumbed powers of coherent light. These are frontiers of science, where new knowledge comes only with the ability to measure new phenomena and express their relationships in numbers. NBS people at Boulder represent a key national resource. Their talents, experience, and esprit de corps are pitted against the frontiers of measurement in the fields of cryogenics, electronics, electromagnetics, time and frequency, and atomic physics. They are responsible for conceiving and developing ways of measuring new, vaguely characterized phenomena. The National Bureau of Standards participates in a major astrophysics laboratory on the University of Colorado campus. NBS scientists, university faculty, graduate students, and undergraduates work together, searching out critical measurement needs and conducting pioneering measurement experiments, feeding the Bureau's rigorous measurement philosophy directly into a young and important branch of science. Creative measurement science is largely responsible for one of NBS Boulder's and the scientific world's most valuable physical assets, the cesium beam frequency and time standard. With this standard, the duration of the second has been realized many times more accurately than any other basic unit of measurement. Capsules of high-purity cesium-133 go into this end of the cylinder. Where a furnace boils them, the atoms travel down the tube at a mean velocity of 20,000 centimeters per second through a very high vacuum. About 1/8 of the atoms are in the two hyperfine energy states pertinent to the standard. The states have opposite magnetic dipole moments. An atom falling to the lower state emits a quantum of radiation. One changing to the higher state must absorb a quantum of exactly the same frequency. The frequency, 9,192,631,770 hertz, is an invariant property of these transitions of the cesium-133 atom. Depending on state, the orientation of the magnetic dipole moment will cause the atoms to respond to a magnetic lens in a characteristic way. This diagram shows the main components of the standard seen from the top, with the lateral scale greatly exaggerated. As the atoms in one energy state reach the first magnet, they change direction. Some atoms deflect right out of the system. The significant part passes through the first microwave cavity, a collimator, the second cavity, and bends once more at the second magnet, missing the detector by a wide margin. The atoms in the opposite state respond in the opposite direction. Neither beam hits the detector. Microwaves are inserted in the path of the atoms. Frequency controls response. When the input matches the critical frequency, the beam suddenly change state, reverse direction of deflection, and hit the detector. The response ceases unless the input frequency accurately matches the frequency associated with a state change, which is a constant of nature. The detector, an incandescent ribbon, ionizes atoms that hit it, generating a current which peaks very sharply when the inserted frequency matches the natural frequency associated with the energy change. Realizing the theory to an accuracy of 5 parts in 10 to the 12th required years of meticulous work, such as producing a waveguide symmetrical within 1,000th of an inch, perfecting the waveform of the microwave input, reducing drift and noise in the data-taking circuits. This standard's accuracy cleared the way for rapid improvements in telemetry, space vehicle tracking, and sophisticated communications. Now, work focuses on even better standards needed for a new generation of electronics: aircraft collision avoidance systems, increased communications channel capacity, improved space, air, and surface navigation, continuing work on the frontiers of time and frequency measurement leads to progress in every technology where time is of the essence. Laboratory astrophysics deals with some of the most fundamental and least understood processes of nature, the atomic reactions in ionized gases. Laboratory investigation of interacting ions, electrons, and photons presents a novel set of measurement problems. Basic problems such as achieving ultra-high vacuum in the experimental environment yield gradually to applied measurement expertise. The cross-beam technique sets up controlled conditions for analyzing the reactivity of unstable species. Beam density and energy can be accurately measured. Here, a beam of electrons plunges through another beam of hydrogen ions. At the intersection, one detector senses desired events plus the background, another background only. Reliable data on atomic cross-sections begins to emerge. A critical need exists for these clear demonstrations of how to measure atomic phenomena. Painstaking reviews conducted and published by the Joint Institute for Laboratory Astrophysics show that only 10% of all scientific papers on atomic collision subjects contain acceptably supported data. Plasma physics, a highly promising frontier of knowledge, urgently requires better measurement methods for accelerated progress on such subjects as interactions of solar radiation with the ionosphere, the electronic and ionic environment of space, a practical approach to controlled thermonuclear reactions. Boulder Laboratories investigates lasers from many aspects. These versatile tools are widely used, mostly on an empirical basis. There is growing need for accurate, compatible methods for measuring laser characteristics. Pulsed lasers, with their varying pulse durations, power, and frequency distribution within the pulse, require special measurement techniques, all of which must be related to the basic units of measurement. Measuring the beam power of a laser requires special approaches. This continuous flow calorimeter traps all reflections of the incoming laser beam. Water flowing in the jacket absorbs the power. Thermocouples measure the heat rise between inlet and outlet. Reliable power measurements figure heavily in the future of laser instrumentation. Some lasers have wavelengths tunable over a wide range. The quantum events associated with changes of wavelength have wide implications in many branches of science. Much work remains before the complex relationships in tunable lasers have been satisfactorily measured and described, and before the laser's potential usefulness in measurement science may be fully realized. The temperature-stable, vibration-free environment of an abandoned gold mine appealed to Boulder scientists as an ideal place to use laser interferometry for an improved determination of the speed of light This experiment uses light from a helium neon laser traveling in a vacuum tube. One amazing difficulty arose immediately. The gravitational pull of the moon moves the bedrock enough to measurably affect the interferometer. Another difficulty touched off a crucial investigation. Lasers are not notably stable as to frequency. This problem was solved by introducing a methane cell in the helium neon laser system, with input tuned to an exact frequency, characteristic of the methane molecule. The output comes to a sharp maximum. This permits stabilization to a few parts in 10 to the 13th. When used for measuring length, the methane device exceeds the reproducibility of the international length standard, the krypton lamp, by a factor of 1,000. The possibility of relating this highly stable infrared radiation to the cesium beam frequency standard poses a solid challenge, engaging many facets of Boulder's capabilities. Time and frequency scientists supply programs used to verify the methane device's stability. Quantum physicists work side by side with electronics engineers on the experiments necessary to multiply known frequencies right up to the infrared. This one step aims at generating the 12th harmonic of a selected HCN laser radiation, mixing it with frequency from an H2O laser, and observing the beat note between them. Everything hinges on harmonic generator mixers that will work at unprecedented high frequencies. The limitations of promising mixer generators are simply unknown. Data gathered in cryogenics research point to the Josephson junction as a strong possibility for producing the critical beat notes. Success at measuring high frequencies might well lead to a firm number for the frequency of the methane device. With this prospective advance, hundreds of length and frequency-dependent investigations outside NBS would move forward. Boulder's cryogenics laboratories deal with measurements on a rapidly expanding scientific and industrial frontier. The commercial manufacture and sale of cryogenic liquids has become a huge business. Accurate metering of fluid deliveries is important to both the buyer and seller and poses a severe measurement problem. For instance, how do you make precise measurements of a boiling liquid? The Compressed Gas Association, producers and distributors of cryogenic liquids, turn to National Bureau of Standards for help. The test facility measures weight changes in the supply and delivery chambers, both in this tank, for comparison against volume meters under test. The experiment helps identify sources of errors, provides a test bed for meter designs, and explores methods of calibrating and testing meters, all toward the goal of measurement accuracy that inspires confidence in this new multi-million-dollar industry. Cryoelectronics facilities deal with the special problems of low-temperature electronics. A dilution refrigerator provides a stable 2/100th degree Kelvin environment for cryoelectronic experiments. Electronic devices operating at cryogenic temperatures exhibit a host of promising behaviors. Their exploitation depends on a systematic program of measurement and data publication. Underlying all of Boulder's many capabilities is a broad, deep experience in measuring radio and higher frequency phenomena. This particular experiment concerns the determination of antenna field patterns, yielding greatly improved data at fractional cost, and in some cases, data not previously obtainable at any cost. Antenna patterns are ordinarily measured from a distance at which the antenna can be treated as a point source. This is the inner limit of the far field. The familiar polar coordinate diagram plots relative field strength as observed from the far field at all angles from the axis. Actual far field measurement means physically carrying an instrument through the field at a distance at least twice the square of the antenna's diameter, divided by the wavelength. For a 30-foot diameter antenna, by no means uncommon, the required distance may be about 6 miles. Far-field measurements made at such distances are very costly and usually give only fragmentary data. At a small fraction of the expense, the complete field configuration can now be determined from measurements made at a very close distance. Boulder has solved the mathematics and designed computer programs that convert near-field data to far-field antenna patterns. Scanning at less than diameter distances yields data like these, which are then transformed to complete maps of the far-field configuration. Dissemination of measurement knowledge is a large part of Boulder's work. The National Standard Reference Data Centers for Cryogenics and Atomic Science gather published measurements on a worldwide basis. The center evaluates data from the standpoints of measurement methods and degree of reliability. Acceptable data go into widely requested standard reference data publications, ready-made measurements, annually saving millions of dollars worth of repetitive effort. Boulder's knowledge of high-purity aluminum and copper is disseminated in the form of samples through the NBS Office of Standard Reference Materials. A major type of dissemination works through calibration of instruments against national measurement standards. Microwave power is ordinarily measured with bolometer mounts. Their calibration requires a careful system of determining corrections for the difference between microwave power input and bolometer reading. These microcalorimeters are national standards for calibrating mounts of different waveguide sizes. A water bath, precise within 25 millionths of a degree, provides a stable environment for the experiment. The readings establish the ratio between temperature rise in the bolometer mount when DC power is applied and when microwave power is substituted for part of the DC. Tested bolometer mounts, with correction factors applied, become working standards used for calibrating mounts in use throughout the country. Mounts so calibrated give accurate, fully compatible measurements, a necessity for designing microwave equipment meeting today's needs for efficiency and operating economy. Dissemination of time and frequency information begins in the clock room, where an array of 5 clocks, 2 of them atomic, keep time. Scheduled comparisons with the NBS frequency and time standard reveal the actual performance of each clock. Rate differences show up as beats, and beat frequency is scaled and punched for computer interpretation. Portable atomic clocks, calibrated for rate and time of day, can be taken to remote locations in need of accurate rate and time synchronization. Radio broadcasts disseminate Boulder's time and frequency information to the entire country via the National Bureau of Standards transmitters at Fort Collins, Colorado. Station WWV transmits on 6 shortwave frequencies, stable to 2 parts in 10 to the 11th. Although somewhat degraded by the propagation medium, WWV's carrier waves are widely used for frequency comparisons. WWVL and WWVB transmit on very low frequency carriers, which travel in what amounts to a waveguide between the Earth and the ionosphere. The signals suffer little degradation by the medium. These transmissions carry the time broadcasts so important to navigation and world time synchronization. The system of disseminating time and frequency standards by broadcast suggests possible future developments. Length standards might one day be calibrated against Fort Collins frequency broadcasts. Somewhere beyond the frontiers of knowledge might lie a practical way of relating temperature and frequency and calibrating thermometers via radio broadcast. Boulder Laboratories host many conferences and workshops each year, disseminating results of latest discoveries in measurement science directly to thousands of organizations whose measurement abilities are fundamental to the nation's scientific and technological leadership. National Bureau of Standards people at Boulder represent a key national resource. Their talents and experience are dedicated to winning and disseminating new knowledge from the frontiers of cryogenics, electronics, electromagnetics, time and frequency, and atomic physics.